This is the second talk about geometric algebra, or Clifford algebra, or GA for short. In this talk I'm going to talk about the vector product, wedge product, dot product, cross product, how they're related, and duality. To recap, recall that the main workhorse axiom of geometric algebra is that squaring a vector gives you the length squared of that vector. This is sometimes called the contraction axiom or the metric axiom. Two consequences of this axiom are that a unit vector squared is 1, and that, or let's say ei for some I equals 1 to n squared is 1. Alternately, ej for I not equal to j equals minus ej ei. Two perpendicular unit vectors anti-commute. Given two vectors, let's say, let's start with 2 dimensions. A vector in 2 dimensions x as x1 e1 plus x2 e2, and a vector y in 2 dimensions y1 e1 plus y2 e2. Squaring this vector, or multiplying these vectors, what do we get? Let's do that. xy is x times y, and I haven't been consistent with my ordering here, but unit vectors and scalars commute, so it doesn't matter. Squaring, we get x1 y1 e1 squared plus x2 y2 e2 squared plus the cross terms, which are x1 y1 x1 y2 e1 e2 plus x2 y1 e2 e1. Because a unit vector squared equals 1, and because perpendicular unit vectors anti-commute, so that equals e minus e1 e2, we get x1 y1 plus x2 y2 plus x1 y2 minus x2 y1, a scalar cross product like term times the unit area element for the xy plane. Now, of course, this can be recognized as a dot product. The bivector term, a term that has an irreducible product of two perpendicular vectors, that is, so we have a bivector plus a scalar as the general result of the product of two vectors. This first, the scalar, we can identify and use the conventional x dot y notation for. We don't yet have a notation for the second beast. Can either define a notation or defer that. I guess let's define it. So this second term is the wedge product. So we could write this as x wedge y. So we have now the product of two vectors xy in a Euclidean vector space is the dot product of those two vectors plus the wedge product of those two vectors. This is a scalar, and the wedge product is a bivector. The sum is called a multivector. In this case, you can have a multivector, suppose M, having scalar components, 3 plus vector components, 7e1 plus bivector components, e2, e3 plus trivector components, e1, e2, e4. This is in some vector space that has dimension at least equal to 4. In this particular case, the product of two vectors is a multivector with only grade 0 and 2 components, where the grade represents the number of irreducible vector products of any given degree. So a scalar is grade 0, a vector is grade 1, a bivector is grade 2, this trivector is grade 3, and so on. Now, looking back, for now our definition of the wedge product and dot product, so we could define the dot product and we can define the wedge product, x1, x2, y1, y2, e1, e2. Those are acceptable definitions of the dot and wedge products. The wedge product will give tidier forms for both. Let's see how this generalizes to higher dimensions. So, for now, let us temporarily work in Rn. I'm going to switch to R3 partway through the process, but some of the results are general enough. I'm off the screen. There we go. Alright, let's define an x as a sum of xi ei's, and define a y as a sum of yi ei, or yj ej, some unique index. I'm going to be lazy with my summation indexes. If I write sum, unless otherwise specified, I mean sum from y equals 1 to n. Now, taking this product, what do we get? xy is the sum of the xi ei's times yj ej's. Split this somewhat. Let's break this sum into the sum of the I equal j terms and the I not equal j terms. So, sum of I equal j, xi, yi, ei, ei, plus the sum of I not equal to j, of xi, yj, ei, ej. Now, this equals 1 is a product of two unit vectors squared, of the same unit vector squared, and this is an irreducible bivector. So in R3, for example, that could be e1, e2, e1, e3, or e2, e3, or any commutation of those pairs of vectors. Now, this, as usual, is just the dot product. Sum of I equals 1 to n of xi, yi times 1 is x dot y. This is clearly, we're going to call this the wedge product as well, but we can first put this into a slightly more tractable form, and to do so, let's use the tensor algebra trick of taking half double the sum. So say xi yj j plus xj xi yj times ei ej plus xj yi ej ei. The second term we can rewrite as minus ei ej, so we're left with dot product of xy plus half of sum of I not equal to j x I y j minus x j y I e I e j. Now we have the same structure almost as the two-dimensional case, and we can make that a little bit tidier by saying it is the sum over all the pairs of ij where I is less than j, and introducing the same determinant notation, which tidies things up a little bit. This is clearly the beast that we are going to define as the wedge product. So now, in Rn, we have xy equals the dot product plus the wedge product. Let's look at some of the properties of the wedge product and examine the implications of this structure. Now we have the determinant factors that are reminiscent of the cross product, multiplied by not by a vector but by a bivector. So each element of the wedge product is a area element as opposed to a normal area element. But because of this determinant structure, or the anti-symmetric structure that underlies the determinant, there's going to be some similarities between these two structures that are obvious right from the get-go. One of those is that the wedge product of a vector with itself is going to be 0. So that is clear since xi, xj, xi, xj for any ij equals 0. Additionally, the wedge product of a vector with another vector has a anti-commutative structure that's similar to the vector product of two perpendicular vectors. In a sense, it generalizes the notion that two perpendicular vectors anti-commute. So y wedged with x is minus x wedged with y. This can be seen by swapping x and y in this expression. Let's just do that. If we swap y with x, we still have the sum over all I less than j, but we have yi ij, xi, xj, ei, ej. Swapping two of the rows or two of the columns of a determinant toggles the sign, so that shows that this equals minus x wedge y. What are the relationships between the wedge and the cross products? In particular, is the wedge product equal to some multivector times the cross product? That's the question to determine. So the answer is yes, and this something happens to be a unit volume element. Let's illustrate how that is the case. And the something will typically be denoted as I equals E1, E2, E3, the unit volume element or the unit pseudoscalar for the three-dimensional space. We can show this by noting that I times E1 is E1, E2, E3, E1, which is E1, E2 minus E1, E3, and now swapping this is minus E2, E1, minus E1, E3, signs cancel out, our E1s multiply together to be 1, and we are left with E2, E3. Similarly, I times E2, E1, E2, E3, E2. You can anti-commute the last two terms, so that becomes minus E1, E2, E2, E3. Those cancel. A final anti-commutation gives us E3, E1. So I times E2 is E3, E1. We have a cyclic index sequence here, 3, 2, 3, 1, 2, 1, 2, 3. And you could probably guess that I times E3 is going to be E1 times E2. Let's show if that's the case. And verify ordering and sign. And that is clearly the case. Those cancel out, multiply to unity, and we're left with IE3 is E1 times E2. IE2 is E3 times E1, and IE1 was E2 times E3. We can now rewrite the wedge product, which was, and I'll repeat, it was determinant of x1, x2, y1, y2 times e1, e2 plus the determinant of x1, x3, y1, y3 times e1, e3 plus the determinant of x2, x3, y2, y3, e2, e3. Now, we have just shown that that is IE3. And this is minus IE2. And this is IE1. Factoring out the i's, we're left with I times x1, x2, let's rewrite this in the right order, x2, x3, y2, y3, e1 plus x1, x3, y1, y3, e2 plus, going to the last here, x1, x2, y1, y2, e3. And we could put this in the conventional form as e1, e2, e3, x1, x2, x3, y1, y2, y3. I, x cross y. To summarize, we've shown that the product of two vectors, x and y, has two components. One component is the dot product, one component is the wedge product. The dot product is a scalar, the wedge product is a bivector. We define the dot product conventionally as the sum of I equals 1 to n of xi, yi, which is a completely symmetric sum, whereas the wedge product is the completely anti-symmetric portion of the vector product. That's the sum over all I less than j of the xi, xj, yi, yj determinants, all scaling the area elements, unit area elements ei, ej. Additionally, in Rn, or in R3, sorry, we've shown that the product of two vectors has the dot product component plus a pseudoscalar scaled cross product component. Scaling the cross product by the pseudoscalar transforms it from a representation of the normal to a representation of the plane itself. So the wedge product xy of xy is a parallelepiped area oriented parallelepiped that lies in the plane of x and y itself.